Hello Chem 241 students, this is Professor James Ormord, and today we're going to talk about the melting point experiment and its usefulness in organic chemistry. You're going to see over the course of the year that melting points are really useful information in many experiments in organic chemistry. And the main thing that we're going to be using it for in this course is it's a really good indicator of the purity of solids. And we'll see here in a few minutes in a little bit more detail, but it turns out that as things melt in organic chemistry, they typically melt over a range of temperatures. So the first temperature we typically record is when the solid appears to look wet, and then it goes through the process of fully melting, and then when it's fully melted, fully liquid, that's the second melting point. And the more pure the compound is, the narrower that range is, and the broader that range is if it's impure. So the overall goals for today's lab is to, the first part, you're going to be exploring how two compounds that have the same melting point by themselves, together, they will actually have a lower melting point range. And then we're also going to be seeing part B that we can use melting points to determine the identity of an unknown. So without further ado, let's go ahead and take a look at the experiment itself. The handout. All right. So here I have the lab pulled up. So here is a picture of the apparatus we're going to be using. The one, depending on which campus you were taking the lab at, your apparatus may look different, but honestly, they're quite the same. Some are programmable, some are not. Essentially, though, all they are is a heating block with a thermometer in them. And and a viewing window, as we see here. And I'll go over that more detail when we actually take a look at the experiment, or actually doing the lab part itself. All right, so you guys may recall from your freshman chemistry courses, I know it seems so long ago now, but during your introductory chemistry course, at some point in there, you should have talked about freezing point depression and boiling point elevation. This is actually the equation that helps explain exactly what is going on here. So, oops, sorry about that. All right, so what we're seeing here is we have the melting point that we observe, the TMP, is equal to, it says TMP naught, or TMP to the 0th. That's basically the pure compound melting point. Or you could think of it as essentially a theoretical melting point, because the temperatures we see in the labs are always a little bit off, but those are your theoretical essentially. And then we have that minus delta T. And what the delta T is, it's basically a change in the melting point due to the impurity. And we'll see here that delta TMP equals KMP times M. Turns out that K is a constant that is unique to that particular compound. Every compound has its own table value for K. And M is the molality. Recall that molality is moles of solute versus kilogram of solvent. So essentially, the more impurity you have, the higher that M value gets, thus the higher delta T becomes, therefore the lower the melting point becomes. And so you get a lower melting point range, and it's also broader. I like to also show this from a graphing point of view, see what that looks like, and make a little bit more sense. All right, so let's go ahead and consider two theoretical compounds that have a similar melting point. So let's just go ahead and say that they're, theoretically 130 degrees. So about 130 degrees C. And then the way we would actually illustrate the effects of melting points with two compounds that have similar melting points is look at how their melting points vary as we mix them together. So what we would do here is we would make a bunch of different mixtures, pure A, pure B, and then 75-25, 50-50, 25-75, etc. So essentially what we can get here is along the graph, way the graph of this data would look, is we would have temperature in degrees C on this axis. And then you can imagine here on the x-axis here, we have %A. And then this will start at 0, 25, 50, 75, and then 100. And then you can think of it with %B, would just the order would flip, right? So at zero, if it was 0% A, at that point it'd be 100. And then the next one would be 75, 50, 50, 75, 25, and then lastly it's just pure A, so 0% B. All right, what we would see happen is that on the ends here, since they have about the same melting point, they should be about equal. There might be a tiny little difference between them because pure compounds can be within 1 degree. Let's just go ahead and say it's 0 for the sake of discussion. But what will end up happening is the melting point will actually lower if you have the impurity in there. So for example, this would drop a little bit here, and then it would drop even further as you had the maximum here for the maximum impurity, essentially 50-50. And then we'd see that as it started becoming pure in B, sorry, more pure in A, that this should go back up like that. So we see a dip here, like that, and then it climbs back up. But remember, melting points are a range, right? So what we see happening here typically is, remember, the more impure it is, the broader the range is. So this can be our T1 value. Remember, that's when it looks wet. And then fully melted should be a little bit higher, right? Because it has to go a little bit more to fully melt. And how far that range is between T1 and T2 will actually be broader in the middle and kind of narrow at the ends. So part of my drawing here, but it should be the broadest here, more narrow as you get towards pure A or pure B. So a big part of this procedure here, part A, obviously, is to you're going to actually generate this graph using data from 2 different compounds. So it turns out that if you read the procedure, that these 2 compounds, urea and tranexamic acid, show up there, tranexamic acid, not on the bottle here, but these have roughly the same melting point. They melt at about 133 degrees. However, if you mix them together, the melting point changes. So we can simultaneously illustrate in part A that you can see the broadening as it becomes more impure. And then you could also potentially use this as a way to determine the identity of an unknown. So for example, suppose you had a solid and it was a white crystalline powder and you thought it might have been urea, or it's one of these 2. You don't know, you're not sure which one it is. We could use melting point to help figure out which one it is. So what you would do is take a little bit of your unknown solid and mix it with urea. Make a little sample with your unknown and urea, and then make another sample with your unknown powder with tranexamic acid, and then get the melting point for both mixtures. And then what you're going to see is the one that is actually the identity of that compound, there should be a narrow melting point range. And then for one that is the incorrect choice, should have a really broad range. So from that, we can, whichever one had the narrow melting point range, that is the identity of the compound. Actually doing this experiment in the lab, you can actually kind of tell which one's which by looking at them and smelling them. But you have to go with the data though, right? So we can't just use our eyes, we have to use our numbers too that we're able to obtain. All right, everybody, before we can actually start doing the actual experiment, one of the first things you need to know how to do is how to actually prepare a sample and how to run the melting point apparatus. So let's go ahead and take a look here. So when you guys grab your samples from the bottles, I recommend that you use weighing paper, wax weighing paper. And then I always recommend that you fold it in half, and then you fold it in half again. And what this does, it kind of puts a little divot in the middle here. So, and it also kind of props it up like this, like almost like a little makeshift weigh boat. So your samples won't fly all over the counter, preferably. And then I also like to, if you're getting multiple solids like you would be in this experiment, I also recommend that you, in the corner somewhere, you label these, because if you have like 30 different white powders on white paper, that you're not going to be able to really tell the difference between them. So for this particular experiment, how much you actually have on here doesn't really matter all that much. It is all that really does matter is that you actually get it inside the tube. So after you have your sample here, oops, I'm not wearing gloves today. Nothing's dangerous here today. So here we have a melting point capillary tube. You may notice here, and I'm showing you really well on the video, but there is a closed end and an open end. So right here is the open end, and then we have a closed end. And then all you do is you simply just tap into the solid. So I like to bunch the solid into a little pile here, and then you kind of just tap it into it. And you may have to, readjust your pile every once in a while as needed. So here, just tapping it into there. I like to go to about a ½ centimeter to a full centimeter in height inside of the tube. And yeah, this is probably enough right here. So you see how the solid kind of got stuck in the top there? And then now we have to get it down to the closed end. The easiest way to do that is just simply tap it on the bench. It actually worked really good with this particular solid, but sometimes the solid will have a tendency to stick at the top here and not actually come down. And the best way to address that is to use a long glass tube. So here we have just a long glass tube, and you just set it on the counter, and then you guys can see this view here. You literally just drop it into it, and then it bounces on the table. You can see it bouncing in there. And this actually works really well if you have once again have a situation where the solid kind of sticks up in the top here. All right, so after you have that, you're then ready for running the melting point apparatus. So let's go ahead and switch over to that. All right, so here is our melting point apparatus. So nothing really overly fancy here. It's pretty much just an aluminum block that has a controller, or aluminum block with a heating element in there. And the particular melting point apparatus I'm using here is programmable. So if you have a non-programmable one, there's literally just a turn dial on there that you just load your sample in, and then you just turn the dial up slowly as you see fit, and then watch the thermometer climb. It isn't all that much different, honestly, with a programmable one, but I'm getting ahead of myself here a little bit. So where you want to go ahead and put the sample is, so here's your viewing window, and then in the top here is the aluminum block that's going to heat up. And then right there in the aluminum block, you should be able to see 3 little holes inside of there. And then all you do is make sure you closed end down where your solid's at, and then you just drop it in there. Like so. Yep, just slide it in there like that, and then you're good to go. And not showing it very well. I'll have a view later, you can see this just fine, but yeah, this is the viewing window. The glare is not doing us any favor there. You can kind of see it a little bit. It's in there. All right. So for the programmable ones, what you want to do is you want to set a start temperature, a stop temperature. That's basically the range at which the instrument's going to run. And then you need to set a ramp rate. So I recommend that you go with about 15 to 20 degrees below what you expect the melting point to be. And then just somewhere above it, doesn't really matter how far above, I usually go about 10 degrees over. So for example, the solid we're melting today is tranexamic acid, which happens to have a melting point of 133 degrees Celsius. So about 15 degrees below, 120-ish, so say 115, just, yeah, 120 should be good enough. So you set your start temperature. So pressing the start temp, and then you have the up and down arrows to program it. So I'll go ahead and set this to 120, which is 13 below the melting point. Oh, I just said 15, right? So let's go 118. You can hold it for it to go faster, or just be patient with it. Oh, it started jumping in 5s after I held it for a while. All right, so there's your start temperature. And then your stop temperature just needs to be somewhere above the melting point. So I like to go with the 10 degrees I said. So let's go to 143. All right, the ramp rate, if you read the procedure, it says you want to try to go for a ramp rate at about 5 degrees C per minute. And I pressed the ramp rate button, it's already at 5, but if you wanted to adjust it for any reason, you can change how fast. Like super slow, normal, and then kind of fast is basically your settings here. All right, after you have all three settings set, I like to double check. So we had our start temperature, 118, stop temp, 143, ramp rate, 5 degrees C per minute. So after you have all that set, this is our start and stop button here. It's toggleable. Every time you hit this, it's gonna toggle between the different modes here. So you wanna toggle it to preheat, right here. And you could potentially do this. I should have done this the other way now that I think about it. But typically you want to go ahead and set this first, and then you want to go ahead and do your sample. So while it's heating up and getting ready, you can do your sample prep, save time, work efficiently. All right, looks like we're ready to go. Temperature's up, sample, we can see it in the view. Let's go ahead and start. So all I did, it's got out of frame right now, but I just toggled the start stop button to toggle this light over to melt. Now the part where you just hang back and wait. What we're looking for here is we are looking for the 2 temperatures here for melting point. Remember, melting point is a range, not a single value. So we're looking at the point where it just starts to melt, and it appears as if the liquid's starting to sweat. It just appears to be, starts to moisten, starts to sweat. That's your first melting point. And then you want to go until it completely melts, full liquid. Depending on if you overpack your solid or not, you may have only the bottom portion that will melt, for example. So if you pack, say, like 2 inches worth of height in there, chances are only the bottom portion is going to melt. So don't wait until the whole thing is going to melt, because it won't do that. All right, you guys catch that? It looks like we're fully melted now. All right, so for this one, we're going to go ahead and melt pure TCA and the 75% TCA. So pure TCA on the left, see it there? And then let's go ahead and put the 75% right next to it on the right. And let's start it. Remember, you want to record a T1 and a T2 the best you can. You want to look at the point where they start to melt, and then when it's fully melted. Looks like we're already almost there. At least the one on the right. All right, we're ready to go for the next one. For this one, we're going to go ahead and do the 50-50 TCA on, or 50-50 TCA urea on the left. Toss that in there. We'll get some focus going on. Hopefully you guys can see it okay. That's better. So once again, that was the 50-50. And then the next one here is the 25% TCA going on the right. You may notice here I set the starting temperature a little bit lower than last time because I have the most impure sample going in, so it should have the lowest melting point of all five samples here. And it did not melt right away the second I put it in there. Had that happen in the past. All right, now we sit back and wait. Just so exciting. Yeah, looks like the 51's already got melted already. All right, we got one more sample to go. Pure urea. Puria? Is that what you call it? No, pure urea. All right, let's go ahead and slap it in there and then hit start. Remember, you want to get the start and stop time, so T1 and T2, where it starts to sweat, and then when it's fully melted. It should be about 133. All right, for part B, we're gonna use melting points to figure out the identity of an unknown. So for this particular part, we think the unknown is either glutaric acid or dibenzothiophenone. We're not sure quite which one it is. They look kind of the same powder-wise. So what I did was I went ahead and mixed a portion of the unknown with glutaric acid, and then a portion of it with the dibenzothiophenone, and then we're going to go ahead and melt it and see which one it is. All right, our melting point apparatus is all set up, and my samples are ready. So on the left side, I'm going to put dibenzothiophenone mixed with the unknown, and on the right side, I'm going to have glutaric acid mixed in with the unknown. All right, make sure we're focused, and we shall start.